All right, we are on our last stuff. So it's going to deal with graphing exponential functions and what they look like. And I know I talked to you a little bit about what exponential functions are, and it's something where a lot of things grow with exponential functions. If you missed yesterday, you have a quiz you have to need to come make up with me, so the sooner the better. So come in on one of your off periods, whether I'm teaching or not, I'll have it. All right, so let's talk about linear functions. Linear functions are straight lines, right? So linear functions, when we graph them, they can look like this and like this. They can be vertical and they can be horizontal, right? And linear functions we do is y equals mx plus b, or we have y minus y1 equals m times x minus x1. Or we even have ax plus by equals c. So those are all forms of linear. So the big thing that comes with linear is the highest exponent on x is a 1. Okay, the highest exponent on x is a 1, which we don't have to necessarily put it. Okay, so far? Everyone has notes, right? Okay. So linear functions, the other things that take place is if you had 2 points, x1 and y1, and x2 and y2, you can find the slope by using this equation. And then usually you plug into point slope to solve. And usually you can leave it as point slope. Point slope is the accepted form to solve a linear equation. We only use slope intercept when we're plugging into the calculator. You doing okay? So you remember seeing this at least once? Vaguely? Good. Can I move on? Yeah. Sophia. All right. So tell whether it represents linear and explain. So I think this one's linear. I think this is linear. I think this is linear. But none of the other things are linear. Why would I say that? What do you think, Aiden?
Because they are squared.
Yeah. So I have an exponent here of a 1. I have an exponent here of a 1. And I have an exponent here of a 1. But everything else here, that has a 2. That has a 3. I don't even know what that is, but I have a square root. So that square root goofs things up. And that's actually the 1/2 power if we wanted to do that. So linear means you have x as a base. It has an exponent of a 1. So normally we have to recognize that x is equal to x to the first. Those are the exact same thing. That okay?
Wait, how come 1 is... Oh, is it because it's squared? I mean rooted?
Yeah, because that's squared, third, and then a root.
Oh, okay.
So they would not make linear graphs. Okay? Can I move on? Then we talked about quadratics. And quadratics are x squared. Okay? So, and when you graph it, it looks like this and like this. If you take Algebra 2, you'll actually see this and this. They just saw that this past week. So it's second semester towards the end of the year, you see that. But you won't see it. Graphs of quadratic functions, you have this, ax squared plus bx plus c equals 0. You can have y minus y1 equals, do I want to do that? X minus h y squared. Actually, I want to erase something here. I want to erase this. Plus k, so that's vertex form. Also, things that happen in vertex form is you have x plus some number. And you could have x minus something else. Okay? So because you have that, if you were FOIL together, multiplied together, you get x squared. So quadratic functions of parabolas. We know that x equals negative b over 2a. finds the axis of symmetry. We negative b over 2a, comma, plug in, finds us the vertex. We have a max, or we have a min. We have roots. That's where it crosses the x-axis. I mean, there's lots of things that we worked with quadratics. And this is where our factoring skill comes from. Quadratic formulas where the quadratic functions where the quadratic formula came from. So we had the song, we completed the square. That was all stuff that has come along with this, okay? Can I move off this? So again, we're just kind of rehashing a few things. So determine if it has a quadratic. So I think this is a quadratic. This is, and this is. This is linear, because that's x to the first. This is cubic, if you wanted to get real fancy. This is raised to the third. So realize x squared, x squared, x squared. Hey, where's the x squared here? Yeah, if you FOIL this out, you get x squared minus 6x plus 8. If you FOILed it out, that's where the x squared comes from. Okay? Seem okay? Not too tough? Can I move on? Whee! Okay, so now we want to talk about exponential functions. So what do exponential functions look like, and what are some of the characteristics? So this is an exponential function. This is an exponential function. This is an exponential function. And how's the other one? That? I think that's it. Oh wait. Nope. I gooped up. Come on, baby. I guess it would be like that. Yeah, that works. Cool. So these grow rapidly. And the thing about an exponential function is, any of you ever have strep throat?
Yeah.
And then they give you penicillin, or amoxicillin, or some sort of cillin. And what that does is it actually, the reason why we can help you with strep throat is it's a bacteria, and we have medications that will take out bacteria. Now, what usually happens with amoxicillin? If you have strep throat and it hurts when you swallow, you have a fever, you don't feel good, take amoxicillin the first day, you still kind of, and all of a sudden you start realizing 2-3 days into it, it's like, I feel like $1 million. I feel better. Now, doctors tell you you need to take the medication for the entire span. Unfortunately, people don't listen to their doctors because, oh, I feel better, so I don't have to take it. And what happened with that is they created bacteria that were resistant to antibiotics. So you made a really mad little bug. So now you have diseases called MRSA, and you have bacterial eating flesh bacteria, which is yucky. And you have, there's just a whole plethora of really bad things that you could catch because people didn't follow the prescribed orders. Why don't you want to take amoxicillin all the way through? Well, you usually have an upset stomach. You're not from it because it's killing off all the bacteria, including the good bacteria that's in your GI tract. That's why you're supposed to eat probiotics, yogurts, and stuff like that when you're on it. But unfortunately, people don't always take the advice. But this is what an exponential function would look like. A and B are numeric values. So A and B represent some sort of numbers. X is the variable. Okay? So the starting point is A. So this is where it would start. And then the growth rate is b, which is the number that is raised to the exponent. So that's the first part of this. So can you already see how it looks a little different? My exponent is a letter now. My exponents before had been numbers, but now I'm actually going to have it as a variable. Cool? All right. So let's see if we can decipher a few things. So this right here is exponential, and this is linear. The reason I know it's exponential is I'm raising it to a number. So things we have to realize is if I were to take 0 and plug it in, what would 2 to the 0, 2 raised to the exponent 0 be equal to? 1. Good. So this becomes 16 times 1. And then if I plug 1 in, I get 2 to the first, which is 2. 2 times 16 is 32. And then if I plug 2 in again, I get 2 to the second, which is 4. 4 times 16 is 64. If I plug 3 in, I get 2 to the third, which is 2 times 2 times 2, which is 8. So 8 times 16 is going to be, I don't know, do it in my head. 8 times 16. It's 48. 4, 128. And then I think I can even go down a little further. If I plug 4 in, I'm going to get 2 to the fourth, which is 2 times 2 times 2 times 2. 2, 4, 8, 16. So I get 16 times 16, so I get 256. If I plug 2 in, I get 2 to the fifth, which is 2 times 2 times 2 times 2 times 2. So 2, 4, 8, 16, 32. 32 times 16, I don't know. Maybe I could do that. So that's going to be 12, carry the 1, 18, 19, 3, 2, 2, 1. Oh, 512, okay. So if we look here, the difference here, that went up by 16, then that went up by 32, and that went up by 64, and that went up by 128, and that went up by 256. So it's growing at a fast rate. Growing at a really fast rate. If we tried the linear, let's see what happens here. If I plug 0 in, I get 2 times 0, which is 0. 0 plus 16 is 16. That's okay. Plug 1 in. 2 times 1 is 2. 2 added that, I'm going to get 18. If I plug 2 in, I get 2 times 2 is 4. Added to 16, 20. If I plug 3 in, 2 times 3 is 6. Plus that is 22, 24, and 26. So this is increasing each time by 2. So which one's growing faster, exponential or linear? Exponential. So if you ever hear of a bank saying, hey, we have a linear account that compounds linearly, run. Don't use them. They're bad. Can I move on? Is this all kind of starting to make sense a little bit? Anything that I've talked about that is unclear? We're good? All right. All right, so steps for graphing. Start at A. That's the y-intercept. So remember, our equation is this. A times B raised to the x. So they're saying, hey, you have A comma 0. That's your starting point. I take that back. The y-intercept. I went flip that over. I went the wrong way. 0 comma A. The reason why it's 0 comma A, if I take 0 and plug it in, B to the 0 is 1. 1 times A. So that's my starting point. As you go to the right from A, multiply times B. As you go to the left, divide by B. Okay, as I go to the right, we multiply by B. As I go to the left, I divide by B. So let's see if we can keep those rules up. I can't split the board anymore. We're not updated. Okay, so let's see. When I have y equals A times B raised to the x, where my B value is larger than 1, it's growth. So this is going to take us growth. And a thing to know about growth is, as I go to the right, my graph grows away. So the math term is as the function, or as x approaches infinity, my function at x goes to either positive infinity or negative infinity. So if it goes up, it's going to positive infinity. It goes down, it goes to negative infinity. But they're both those cases are growth, because they are growing away from our origin, or growing away from something they call an asymptote, but we're not there yet. These are decay. And so as I go to right, my graph comes to the asymptote. But we'll talk about that. So that's the asymptote. So this says as x goes to infinity, the function at x goes to, basically we'll just call it 0 for now, is what it's really doing. And I'm just writing the functional notation so it's there, so we look all fancy, nice and neat. Am I doing okay? All right, where are we at? All right, we're ready to start graphing. Okay. So I want to graph this first. So when we need to graph something, maybe we think about kind of a t-table. So we might try this, and we might say, hey, if I start with 0 and I go to 1 and go to 2, maybe that might be enough, but I don't know. So 2 to the 0 power is what? 1. 1 times 4 is 4. So I get 0, 4 right there. Is that okay? If I plug 1 in, I get 2 to the first. 2 to the first is how much? 2 raised to the first power is what? 2. 2 times 4 is 8. 1 times 8, 1, 2, 3, 4, 5, 6, 7, 8. And if I plug 2 in, I'm going to go off the graph because I get 2 squared, which is 4. 4 times 4 is 16. So I'm already off the graph at 2. But let's go the other way. -1. How do I write this? We just tested on it. It's the negative exponent, so what does Ron do? Go below, good. So that becomes 1/2. So 1/2 times 4 is 2. So -1, 2. Let's take the -2 and plug it in. So I get 2 to the -2. What's that going to become? 1 over 2 squared. What's 2 squared? 4. So I get 1/4. So 1/4 times 4 is 1. -2, I'm at 1. If I keep going, it's going to do this. Hey, can I keep plugging in numbers and get stuff out? If I plug anything bigger than 2 in, my numbers are going to start getting pretty big, but do you think they still exist? Hey, what was the domain? Domain relates to x or y? X. Okay, so my domain on this is going to go from negative to positive infinity. My range deals with the y's. Do you think my graph's going to go forever up? In this case, it will. Is it starting from someplace down here? Yeah, it's starting from 0. Do you think I'll ever cross 0? No. Okay, so that's my range. Okay, so remember the range is an elevator going up and down. So this is definitely a growth chart. T-table is a good thing. Let's see, what does it say down here? What is the difference between these two graphs? I don't know. I didn't have two graphs. Question mark. I don't know. I forgot to put a graph on there, I guess. Let's go to this one. Whoops. I went backwards, didn't I? Here. Here. There we go. All right. So let's try and do this off my one graph. Let's see what they had some rules back here, right? Start at A. So 0, comma A. So A doesn't have the exponent, right? So what's my A value on this one? 2 has an exponent. 1. So at 0, comma 1 is where I'm going to start. It's right there. And then what else did it say? It said, as you go to the right from A, multiply by B. Ooh. As I go to the right, I'm going to multiply by B. Let's see if we can make that work. Multiply times B. So if I multiply that Y value times B, I'm going to get 1 times 2 is 2. 2 times 2 is 4. 8. 2, 3, 4, 5, 6, 7, 8. If I go this way, I divide, so that's going to be a half, then a fourth, then an eighth, then a 16th. Ah, so that's what this one looks like. Let's try the second one. The second graph, what's my first point I plot?
1.5.
Yeah, so 0, comma half, right? 0, comma half, so it's down here a little bit. And as I go to the right, I'm going to multiply by 2. So what's half times 2? 1. What's 1 times 2? 2. 4. And then 8. 3, 4, 5, 6, 7, 8. If I go this way, it's still going to do this. Huh. So describe the domain and range of both. The domain will be negative to positive infinity on both because I can go forever left and forever right. But my range on both will go from the x-axis 0 to infinity because they're going up. So what does the difference between the two look like? It looks like the blue one's a little maybe wider or maybe shifted. But essentially they're the exact same graph. Let's see if we can move to the next one. Okay. What did the words tell us to do? What's my very first point on this graph? So 0, comma what? 4. So if I plug 0 in, I get 1/2 to the 0, which is 1 times 4. So 0, comma 4. And as I go to the right, I'm going to multiply by half. Half of 4 is? Half of 2 is? Half of 1 is?
1/2.
1/4, 1/8. Okay. This graph's doing this. This is decay. Why is it decay? Because this value here that's being raised to the exponent is between 0 and 1. So we have decay. What about this graph though? What's my first point I plot? A, which is what? -1, so 0, -1. 0, -1 right there. As I go to the right, I'm going to multiply by half. As I go to the right, I'm going to multiply by half. Half here. Wait a minute, that's kind of weird. Let's see, if as I go to the left, this is going to go down this way. 4. Look at that. These are both decay graphs. They're both decay because they're both coming to the x-axis. So my domain on both of these, let's do the domain on the blue first. Actually, they both have the same domain, negative to positive infinity. But let's do the range of the blue. Where am I starting from? So I'm riding an elevator up. Tell me when I get to my blue graph. There. And it keeps going, right? So my range here is going to go from 0 to infinity. But my green graph, do I see my graph here? And where do I stop? There. So my green one goes from negative infinity to 0. Different. Very different. Why did one flip over? I'd say that negative out in front had something to do with it. Both those are... All right, let's see. We want to say if they are linear or exponential. So it looks like I'm adding 2. And that's definitely linear. And then the next one, I bet you're right. Add 4, add 8, add 16, exponential. Yeah, buddy. Cool. Did you submit it?
Yeah.
Thank you. One more? One more page or one more graph? One more graph. Okay.
Thank you, Mr. Chair.
You got it. I'll let you know 8th period how you did.
Okay.
All right. Ooh. Okay. Huh. Wait a minute. All right. Ooh. Okay. So this is our graph. Let's see what we got here. It says the graph represents a bacterial population Y after X days. So your days are being on the x-axis, 1, 2, 3, 4, and in the y direction are how many there are. Write an exponential function that expresses the population. Find the population after 12 hours and after 5 days. So these are in days, right? Okay. All right, so let's get our exponential function first. So I know I have this. Agree? Okay. And I know that my a value has to be 0, 3. So it's got to be a 3. Do you agree with that? And then I have to find my b value. Okay. So from 3 to 12, I had to multiply by what? 4. So now I get 4 to the x. Okay, so let's make sure we make that work. If I plug 0 in, I get 4 to the 0, which is 1. 1 times 3, which is 3. That works. If I plug 1 in, 4 to the first is 4. 4 times 3 is 12. If I plug 2 in, that 2 right there, 4 squared is 16. 16 times 3 is 48. Okay, this is our exponential function. Okay. Find the population after 12 hours and after 5 days. Okay? So what is my graph? How can I do 12 hours? 12 hours is how much of a day? Half a day? 0.5 of a day? So if I wanted to figure out my growth on this, I'm going to go 3 times 4 to the 0.5. Ooh. So 4 to the 0.5, that means the square root of 4, which is 2. 2 times that, oh, okay, 6. And then after 5 days, okay, 5 days, I'm going to go y equals 3 times 4 to the 5th. Anybody have any idea what 4 to the 5th power is? 4 times 4 is 16. 16 and 16 is 256. 256 times 4. 256 times 4. Let's see, that's 24, 20, 22, 2. It's 8. 1,024. 1,024 then times 3. Yeesh. 3,076 bacteria. Whoa. I just did the multiplication. I'd say you definitely would want probably a calculator to do that. Huh. Is bacteria good or bad? Both. Good. I like the answer. You need it. There's healthy bacteria that helps you survive, and then there's unhealthy bacteria that makes you sick. Okay? Does anyone want to know what the difference between a bacteria and a virus?
Yes.
Do you know how big a virus is in comparison to a bacteria? What's bigger?
Virus.
Oh, virus is tiny. So here's your best representation. I heard this in a pre-medical class. A bacteria would be the size of the football field. The virus would be the football in the middle of the football field.
That's why it's like so hard to detect or something.
Yeah, it's hard to figure out. Yeah.
Why are they so dangerous? Is that a weird word thing?
Well, they actually don't feel viruses actually were part of this planet. They feel that because it's a crystalline structure that changes the messenger RNA and messes with things in your body. So they don't even feel that a virus is actually from Earth. They think it was something from someplace else, almost extraterrestrial. That's one theory out there.
You don't get
Like,
Yeah,
What's the difference between like human bacteria and yogurt?
nothing. It's just bacteria is bacteria. They I mean, genetically, if you look under a microscope, bacteria is going to kind of look like that. No matter what you're looking at, you'd have to look at the DNA of it to decipher what it is. Yeah, we do have homework. You guys want a lot of homework tonight?
No.
Cool. All right, we'll do a lot. Man, this guy's not fun anymore. So. Alright, what do you say we do page 157, 158. Page 157, 158. Evens. You're not sure how to do evens, then do them all, and I'm sure you get the evens in there. Cool? All right.